Welcome back. In our first video, we talked about the mechanisms of phase transformations and the key factors affecting the nucleation and growth of a new phase. We saw there was an optimum undercooling where the rate of transformation is maximized. Now we'll quantify the time it takes to complete the transformation at different temperatures, how to generate plots of the fraction of the phase conversion as a function of time and temperature, and how to read and use the resultant time-temperature transformation, or TTT diagram, by using the solidification of liquids as our primary example. In the second part of our videos on phase transformations, after a brief recap of the main parts of Part 1, we'll look at the transformation times and generate so-called S-curves that represent the extent of transformation as a function of time. We'll quantify the dependence of the S-curves with temperature and undercooling and generate time-temperature transformation, or TTT, diagrams for the solidification of liquids. We'll look at how the solidification proceeds at different cooling rates, and also explore the formation of glasses when samples are quenched very quickly. Let's begin with a quick recap of the main points we covered in our first video. We discussed the mechanism for phase transformations that proceed via a process of nucleation and growth. Using the solidification of liquids as our example, and here we're looking at the crystallization of a polymer from its liquid, we noted the growth of crystals can only proceed after an incubation period where atoms stick and organize in nanometer-sized nuclei that must reach a certain critical size prior to growth of the new phase. We saw the importance of the degree of undercooling below the equilibrium freezing point and showed the required critical size of the nuclei decrease with increased delta T. As a result, as the undercooling increases, the rate of nucleation increases, more nuclei are produced, and the final size of the solid grains will be smaller than those produced from smaller undercoolings. However, at very low temperatures, the nucleation rate begins to decrease when the atoms have very limited mobility. As a result, the rate of nucleation is maximized at a given undercooling. The rate of growth also depends on the undercooling. Now, growth is a diffusion process, and while the diffusion coefficient always favors faster growth at higher temperatures, i.e. a lower delta T, the driving force for growth shows an inverse effect and favors increased growth at lower temperatures. Combined, these two effects also lead to an optimum undercooling to maximize the growth rate. The maximum for the growth rate always lies at a higher undercooling compared to the nucleation rate. Finally, we showed the overall rate of the transformation given by dx dt, where x is the fraction of the new phase that is formed, is proportional to the growth and nucleation rates, and it has a maximum that lies between those for g and I. And so if we want the transformation to take place in the fastest possible time, that is where we want to be as far as the undercooling is concerned. We'll now move on to look at the time it takes to complete the transformation at different temperatures, and we'll generate so-called S-curves that relate the fraction of the new phase formed, x, to the time taken for the transformation. And we'll then generate and read the so-called TTT diagrams. On the left we have our sketch of the rates for growth, nucleation, and the overall rate of conversion as a function of temperature. We'll pick a temperature, and on the right we'll plot the fraction of the phase transformed as a function of time. Let's start with T1, which is the optimum undercooling temperature for the fastest overall transformation. The phase conversion starts with the formation of nuclei. Although at this temperature it doesn't coincide with the fastest nucleation rate, it'll still be quite rapid, and we can plot the relative time the nuclei will take to reach a critical size on this right-hand plot. We should note that right now there is no actual phase conversion occurring during the incubation period, i.e. X remains at 0. It's just the sticking of atoms and their organization into embryos. Now growth begins, and we are not at the peak of the growth rate, and while the growth time will not be the fastest possible, we can sketch the relative change in X from the start of growth to its completion, where X is equal to 1. During growth, the change in X with time will always follow this S-curve profile, with a slower start, faster conversion halfway through the transformation, and then a slower finish as the old phase is completely consumed. We can highlight the time taken for the growth process shown here. The time for completing the entire transformation, from the beginning of nucleation to the end of growth, is shown up here. Because we picked a temperature where dx dt is a maximum, this will be the shortest possible overall conversion time. However, it is only during the growth period where we would be able to detect and observe the formation of crystalline solid grains, for example by using X-ray diffraction. And so it's only during that period of growth that we could monitor the change in X with T. It's important to recognize that during the incubation period there are no actual solid crystals and the sample is still all liquid, albeit with nanometer-sized embryos that are attempting to organize. Just to make sure we're clear on the different stages of the transformation portrayed on this diagram, we'll label the different phase regions in the S-curve at this temperature. First, during the nucleation period, nuclei are continually attempting to form and strive to reach a critical size. But the sample is still a single-phase liquid that has been preserved by the undercooling. During growth, the crystalline solid grains formed from the nuclei grow and consume the liquid phase. So in this region, the sample is two-phase, solid plus the remaining liquid. As we noted earlier, the rate actually slows down as X approaches 1. This is due to the smaller volume of remaining liquid, and therefore less nuclei, and the impingement of the solid grains. The sample is only single-phase solid after the completion of the growth. The profile of the S-shaped growth curve, the change in X with time during growth, can be quantified by the so-called Avrami equation shown here. The equation contains two transformation-specific parameters, K and N. N depends on the geometry of the crystals being formed, and its value is actually 1.5 if those are spheres, while K depends on the actual material and temperature. By convention, if we were to quote a rate for the reaction, one uses the time for 50% conversion shown here. The S-curve we plotted to represent the overall dependence of the transformation was for a particular temperature. We actually chose the temperature where the total transformation time was the fastest. By looking at the conversion rates at all possible undercoolings, it's possible to map the observable, i.e. the start and finish times of the growth at all temperatures. That enables the generation of a time-temperature transformation, or so-called TTT diagram. So now we will select different undercoolings, plot the extent of the transformation and the S-curve at each temperature, and map the growth start and finish times at each one. On the left we have our growth, nucleation or incubation and overall transformation rates as a function of T. Let's pick a temperature. We'll start with the one in purple, where the overall rate is the fastest. And at the top, we'll plot the corresponding S-curve and indicate the time for nucleation and subsequent growth by adding the start and finish times for the growth, like that. So up to here, nucleation. This is the growth period. We're using a log time scale just so we can represent a broader range of times. Now at the bottom, we'll transcribe the start and finish times for growth at that temperature onto a plot where our y-axis is temperature and x-axis is still time. We'll pick a higher temperature, shown in orange, with less undercooling, and sketch the S-curve at that temperature. At this temperature, the nucleation and growth rates are slower. You can see here. Growth rate's quite slow, and so's the nucleation rate. And so the time for both are longer. Longer nucleation compared to before. Longer time for the growth to be completed. Again, we'll add those start and finish times to the temperature time plot in the lower diagram, here and here. Now we'll go to a much lower temperature, a much higher undercooling, shown in brown. Here, the rates of nucleation and growth, they're even longer. Let's indicate them on the top diagram. And again, we'll map these onto the bottom plot. By doing this at several different temperatures, we can map out a start curve and a finish curve for the transformation at all possible undercoolings. These so-called C-curves provide a map of the time temperature transformation TTT diagram. The nose of the curve, right here, corresponds to the temperature with the maximum rate, i.e. the fastest transformation time. Before we use these maps, let's again make sure we can identify the different phase regions on the TTT diagram. Region A, at a temperature above the equilibrium freezing point, is where the liquid is thermodynamically stable. Area B is the region of nucleation, where the liquid is present, though not stable, but no crystalline solid has formed. So this is a metastable liquid, meaning it exists or is preserved as a supercooled liquid, but those nuclei are forming and organizing. Area C, this is the region where the growth is complete, the transformation to the stable solid phase is finished. Area D, between the start and finish curves, is where the solid grains are growing and both liquid and solid are present. What about region E? Here we have unstable liquid, but the temperature is so low that it would take extremely long times for any crystals to form. So here the liquid can be preserved, perhaps indefinitely, and we label this as an undercooled liquid. Now we'll use the diagram to predict what will happen when a liquid is cooled down from a temperature above the melting point. To do this, we'll superimpose different types of cooling curves and map the reaction as a function of time. First, let's consider a sample that is slow cooled. Here we add the cooling curve. We could quantify the actual rate of cooling if we wished. And we'll compare this to a sample that is cooled from the same temperature, but at a faster rate. We'll call that fast cooling. Using the TTT diagram, we can read off the start and finish times and the temperatures for the slow cool sample and compare them to the fast cool sample. It is evident the fast cool sample has a quicker start and finish. With its longer start time, the slow cool sample has a longer nucleation time. This slower nucleation is because the incubation is occurring at a smaller undercooling and requires larger sized nuclei to begin the growth. As a result, fewer nuclei will form, and the final sample will be comprised of less but larger grains. The faster cool sample, in contrast, has a shorter nucleation period. The nucleation is occurring at a higher undercooling, where the lower critical size for the nuclei produces many more nuclei, and the final solid sample will comprise many more but smaller grains. What will happen if we cool a sample so quickly, which is called quenching, that it bypasses the nose of the C-curve? Now the undercooled liquid is frozen. Even with time, the nuclei can never reach a critical size, and crystallization will not take place at all. So what is this? It's a glass, or an amorphous solid, i.e. a frozen liquid. I'm sure you're familiar with the many applications of glasses, particularly those used in windows, which are complex oxides based on silica. You may not be as familiar with electrically conductive metallic glasses, which require very rapid cooling rates to preserve a glassy state. The critical quench rate, as it's called, to bypass the nose and form a glass, can be quantified from the TTT diagram. For simple metal alloys, a quench rate greater than 10 to the 5th degrees per second are required to avoid crystallization, as their simple close-packed structures can organize and form very quickly. With those rates, it's not possible to produce a bulk sample of glass, although very thin glass ribbons and films that cool quickly can sometimes be made. However, bulk metallic glasses can be formed for multi-component alloys, with multiple atoms of different sizes, which are harder to organize into a regular solid lattice. In particular, the so-called vitrolloid glass, with mixtures of zirconium, titanium, copper, nickel and beryllium, have been developed, where the much slower quench rate allow the fabrication of bulk samples in metallic glasses in reasonable times that allows a bulk sample to be cooled in the glassy state. These are an interesting family of conducting glasses that have very high strengths and outstanding corrosion resistance. Finally, we should clarify the difference between homogeneous and heterogeneous nucleation. Everything we have discussed is called homogeneous nucleation, where the nuclei form in the bulk of the liquid, and the incubation does not involve impurities or defects. Here, solidification can require significant supercooling, often between 80 or 300 degrees C. However, many transformations proceed via heterogeneous nucleation, which occurs on pre-existing nucleation sites, such as impurities or the walls of the container. Because there is less volume required for the nuclei, for example, half a sphere, if you like, on a surface, the barrier to nucleation is reduced, and the supercooling can just be a fraction of a degree. In the first part of our videos, we also saw the nucleation barrier could be overcome by adding a pre-formed seed crystal. We saw this when supercooled water froze spontaneously when it was poured onto a pre-made ice cube. In many systems, the nucleation will also be favoured at other types of defects, such as surfaces, grain boundaries, or dislocations. We'll continue our discussion in part 3, the final video of this series, where we'll look at TTT diagrams for all solid phase transformations in the iron-carbon steel system.